Throughout history, humanity has never been free from infections, epidemics, and pandemics. In this video, we explore how advancements in diagnostics technologies can transform our ability to detect, respond to, and prevent pandemics. If you take a look at the history of pandemics, this includes Black Death, Spanish flu, and recent COVID-19 pandemic. It has continuously impacted various aspects of our lives such as the economy, society, culture, and life. And is this end? The answer is no. There will be 2 more pandemic expected to hit us. One from respiratory viruses like COVID flu RSV. The other from bloodstream infections like sepsis. Respiratory virus-based pandemics will be accelerated by 3 key factors. Deforestation, as forests are destroyed, wildlife habitats are disrupted, leading to increased interactions between humans and animals. This elevates the risk of zoonotic diseases, viruses that jump from animals to humans. As we come into closer contact with previously isolated species, the likelihood of new respiratory viruses emerging and spreading grows. The second is globalization. In our highly interconnected world, globalization has amplified the speed and reach of disease spread. With international trade, tourism, and business travel at an all-time high, viruses can cross borders rapidly. A localized outbreak can become a global pandemic within days due to the constant flow of people and goods across countries, accelerating the transmission of respiratory viruses worldwide. What starts as a local outbreak can quickly escalate into a global pandemic, as seen with the rapid transmission of the Alpha, Delta, and Omicron variants. Globalization not only accelerates the spread but also contributes to the evolution of new variants as the virus encounters diverse populations and environments, making containment and control much more challenging. The third is, as global temperatures rise, ice caps and permafrost are melting at an accelerated rate. This thawing releases ancient viruses that have been trapped in the ice for thousands of years. These sleeping viruses, once dormant, can emerge into the environment, and because no living species, including humans, have immunity to these ancient pathogens, they pose a significant threat. The reintroduction of these unknown viruses, combined with our modern, highly connected world, could potentially spark new pandemics, creating challenges for public health systems that have never encountered such pathogens before. Based on these 3 factors, researchers estimate that we currently face a 2% chance of experiencing a COVID-19-like pandemic in any given year. This means that by 2050, there is at least a 40% chance that we will face another pandemic of this scale. By 2075, that likelihood jumps to 64%, and by 2100, the risk is estimated to be 78%. While these numbers reflect probabilities, another pandemic is almost inevitable unless we actively change the future. One of the looming threats is antimicrobial resistance, AMR, especially within the field of bloodstream infections. The first contributing factor is the misuse and overuse of antibiotics. To explain the problem, let's imagine there are both antibiotic-sensitive pathogens and antibiotic-resistant ones. When antibiotics are misused, whether by overprescribing or using them incorrectly, we aren't just killing off the sensitive pathogens, we're creating an environment where only the resistant pathogens survive and thrive. Over time, this misuse essentially replaces all the sensitive pathogens with resistant ones. This is happening in agriculture and hospital very rapidly, and we are trapping ourselves in a vicious cycle. Every time we develop a new antibiotic, we create a temporary solution, but misuse and overuse quickly make it useless. The other contributing factor is lack of new antibiotics. There was a golden era of antibiotic discovery between the 1940s and 1970s, when many groundbreaking antibiotics were found, transforming the treatment of bacterial infections. However, after 1970, the discovery pipeline slowed significantly, and few new antibiotics have been developed. Pharmaceutical companies have been reluctant to invest in antibiotic research due to high costs and the quick development of resistance, leaving us vulnerable to resistant infections. As a result, it is expected that by 2050, these factors could cause up to 10 million deaths every year. As a reminder, the total death from COVID-19 was 7m. This means that simple infections, which were once easily treatable, could become life-threatening because we no longer have effective drugs to fight them. Can technology save us? Yes, technology, especially diagnostic technology, offers us a powerful equipment in the fight against both respiratory and bloodstream infections. How does diagnostic technology work? Every living organism has its own unique genetic code, whether it's DNA or RNA, unique to themselves. Diagnostics rely on identifying this unique code to detect specific pathogens, such as viruses or bacteria. However, in real samples like blood or saliva, the DNA or RNA of pathogens is often buried beneath a lot of impurities, making it difficult to detect directly. One powerful technique we use is called target amplification. Since the amount of pathogen genetic material is usually very small, we amplify it by creating billions of copies of a specific DNA or RNA sequence. This amplification process allows us to easily distinguish whether the pathogen is present or not. Essentially, it turns the problem of detecting a tiny amount of genetic material into a situation where you're comparing either nothing or billions of copies, making the result much clearer and easier to interpret. The most well-known technology for this is polymerase chain reaction (PCR). The current diagnostic process is shown below. Patient feels sick and visit hospital. Samples are collected from the medical personnel. Diagnostic is performed and, based on the result, you decide either to visit grandmother's house or do self-quarantine. The problem is the diagnostic results doesn't make it back to patients or they become available after the decision windows. The major bottleneck is delivery to the lab. Because sample collection and lab testing only takes less than 2 hours, but you have to wait a couple of days because samples should be delivered to centralized lab equipped with benchtop machine. So if we can remove this delivery, we can reduce the diagnostic time less than 30 minutes. The opposite concept is point-of-care diagnostics. These tools allow us to test for diseases right at the site of patient care, without the need for complex lab equipment or lengthy processing times. These tests can be done in clinics, hospitals, or even at home, offering quick results that help doctors make immediate decisions. It is basically delivering the lab to patient. On the other hand, by 2030, 1 in 6 people will be over the age of 65, a demographic shift characterized by reduced physical activity. 90% of this population will have at least one chronic disease. For this aging population, healthcare should focus on disease management rather than striving for 100% cure, as managing chronic conditions will be key to improving their quality of life. Many elderly individuals will fall into the middle-income category, where the rising costs of healthcare become a significant burden. As a result, there is a growing expectation for healthcare to shift toward consumerism, where patients demand more affordable, accessible, and personalized care options. This is where translational research comes into play. By changing the paradigm with point-of-care diagnostics, we can provide rapid, accessible, and affordable testing that fits the needs of an aging population. An example of point-of-care diagnostics: in our lab, we've developed a smartphone-based diagnostic method that brings the power of traditional lab equipment, like a PCR machine, into a portable, accessible format. The bulk PCR instrument performs 3 key functions: temperature control for the reaction, fluorescence reading to detect results, and maintaining a contamination-free, closed system. We've translated these complex functions into a more compact and user-friendly system using a 3D printed cartridge and a cradle-based smartphone reader. We replaced the temperature control with simple heater, small LEDs, and filters for fluorescence reading by smartphone and 3D printed microfluidic system. This portable device allows for rapid, on-site diagnostics without the need for large, expensive lab equipment. We've added even more value to our smartphone-based diagnostic system by integrating not only COVID-19 identification but also the ability to identify variants. SARS-CoV-2 has multiple genome segments, with the S gene being highly mutable and the N gene remaining conserved, or unchanged. Using a duplex double detection system, we can simultaneously target both genes, allowing for accurate identification of the virus and any variants in under 30 minutes. This dual functionality makes our system not only faster but also more comprehensive, providing crucial information for managing ongoing viral outbreaks. As COVID-19 cases began to decrease, we noticed a rise in other respiratory viruses like the flu and RSV. In response, we extended our system from a duplex to a multiplex platform, now equipped with 6 detection reservoirs. This allows us to detect up to 4 viruses simultaneously using just a single swab. Additionally, we've incorporated lyophilized, freeze-dried, reagents that offer longer stability at room temperature. This means our diagnostic platform no longer requires a cold chain for transport, making it easier and more cost-effective to deploy in various settings, especially in resource-limited environments. If we think about the generations of diagnostics, the first generation would be something like a lateral flow test, similar to a pregnancy test. It uses simple chemistry, like antibody-antigen binding, which is very fast and inexpensive, but it's not always the most sensitive or accurate. The second generation brought nucleic acid detection, which is more sensitive but requires multiple steps. To streamline this, people began using microfluidic devices to separate each step, but this added cost and time. Now, the third generation is moving toward smaller, palm-sized devices, where detection happens directly from the sample. These devices can detect single pathogens in less than an hour but are still somewhat costly. Our point-of-care system falls between the second and third generations, simplifying processes while maintaining high sensitivity. If you think about the next generation of diagnostics, it could be wearable or implantable, offering multiplexing capabilities to detect multiple pathogens quickly, cheaply, and routinely. Achieving this future will require expertise across various disciplines within bioengineering and biomedical engineering. This is why it's crucial to grow and nurture the next generation of diagnostic leaders in these fields. Perhaps one of them will be you. Let's switch gears and dive into bloodstream infections. The amplification process I mentioned earlier works like this. The target DNA is copied exponentially, creating billions of amplicons, which make detection possible. The great thing about this process is that many companies already sell amplification master mixes, so theoretically, you could just take a blood sample and add it to the mix for diagnosis. But here's where it gets tricky. When you're dealing with blood, there are numerous background impurities, proteins, hemoglobin, and other components that can interfere with the reaction. These impurities can bind nonspecifically to all the components in the reaction, making it difficult to get clear results. This is one of the biggest challenges we face in developing blood diagnostics, and it's why direct molecular detection from blood remains so complex. To overcome the interference from blood impurities, diagnostic procedures typically start with a purification step. This involves binding the target DNA to something using magnetic force, which allows the removal of background impurities while leaving the DNA attached. Once the impurities are removed, the DNA is eluted with a clean buffer. But here's the catch: this binding and unbinding process isn't 100% perfect. With so many impurities in the sample, some target DNA inevitably gets lost. This loss becomes more problematic when you start with a low concentration of DNA because the recovery efficiency drops significantly. The lower the starting concentration, the more DNA is lost, which is a major issue in cases like sepsis or bloodstream infections. For example, in a COVID-19 sample, there are typically 100 to 1,000 virus particles per microliter of fluid. In sepsis, however, you may only have a few bacteria in an entire milliliter of blood, 1,000 times less DNA in 1,000 times more volume. In this scenario, after purification, you could end up with almost nothing left, making diagnosis extremely difficult. There is no way to start with purified DNA. To ensure there's enough starting DNA for detection, the current gold standard for diagnosing bloodstream infections begins with an enrichment step called blood culture. In this process, a sample is placed in a bottle that provides a favorable environment for pathogens to grow. The bottle is then put into a large instrument, which looks like a refrigerator, where the temperature and other conditions are carefully controlled to encourage growth. The instrument monitors the sample and sends an alert when growth is detected. This method helps increase the amount of pathogen DNA in the sample, making it easier to detect. However, it's a time-consuming process, often taking days to get results, which is a significant drawback, especially in critical cases like sepsis where rapid diagnosis is essential. However, there's a major problem with relying on blood culture for sepsis diagnosis: it's too slow. Every hour that passes during septic shock increases the mortality risk by 7.6%. Because time is so critical in sepsis, doctors often have no choice but to prescribe a wide range of antibiotics immediately, hoping that one of them will be effective against the infection. This is done without knowing whether the sepsis-causing pathogens are resistant to any of the antibiotics. As a result, this practice leads to overuse and misuse of antibiotics in clinical settings, fueling the problem of antimicrobial resistance. Unfortunately, this reactive approach has been the standard practice for over 40 years, creating a vicious cycle where slow diagnostics push the need for broad-spectrum treatments, contributing to resistance and weakening our arsenal of effective antibiotics. Can we skip purification and culture? Can we use all DNA in the sample without loss? Let me introduce a new approach developed in our lab called the biphasic method. This process uses blood drying to bypass the traditional purification and culture steps, enabling us to use the entire blood sample without any DNA loss. Here's how it works: after drawing the blood, we simply dry the sample. During this process, we create micro and nanofluidic structures within the dried blood, or blood cake, allowing reaction mixes to pass through. The reason it's called biphasic is that two distinct phases are formed: a solid phase, the blood cake, and a liquid phase. Enzymes and reaction components diffuse into the blood cake, searching for the target DNA. Once found, amplification begins, and the resulting amplicons diffuse out. We then read the fluorescence signal from the top without interference from the red heme background. This method allows us to use all of the DNA in the sample, without the need for purification or enrichment steps, making it an affordable and efficient solution. One of the most exciting things about the future of diagnostics is that it's not just a job for biologists or doctors. The advancements we're seeing today come from the intersection of many different fields: bioengineering, materials science, molecular biology, and artificial intelligence. Each discipline brings its own expertise, and together, they are driving innovation in ways we couldn't have imagined just a few decades ago. Call to action: empowering the next generation of innovators. As we look ahead, one thing is clear: the future of healthcare, diagnostics, and even global health is in the hands of the next generation. Maybe that's you. The advancements we've talked about today, wearable diagnostics, artificial intelligence, and rapid pathogen detection, didn't happen overnight. They were the result of years of hard work, curiosity, and collaboration by scientists, engineers, and healthcare professionals. But the fight against infectious diseases, antimicrobial resistance, and future pandemics isn't over. In fact, it's just beginning. So, I encourage you, stay curious, ask questions, and don't be afraid to explore new ideas. Whether it's in a lab, a classroom, or even on your laptop, the next big breakthrough could come from you. Let's work together to create a healthier, more sustainable future. Thank you for watching, and let's continue the journey toward a better tomorrow.